All right, hey, let's look at 5.1, and it is all about taking derivatives of natural log functions. So first we catch a little background on natural logs, and I believe you remember some of it. We've covered it earlier in the year, but properties of natural logs, we realize that the domain is from x being just slightly bigger than 0 up to infinity. The reason for that is if I try to do the natural log of 0, it's asking me to find a power that I can raise e to come up with 0. And that would be very difficult to do because the 0 doesn't even equal 0, it equals 1. So that is the reason for the open parenthesis on the 0. The range, however, can come out to negative infinity or positive infinity. And we see that where the function continues to go downward and continues to climb as my x values get larger. This function is known as a one-to-one function. Every x has exactly one y, and every y has exactly one x. Also, it is an increasing function. The tangent lines or the slope of the function are always positive. It is a concave down function. So we can see that the first derivative is decreasing as we move to the right, meaning we get the downward bend, a concave down. Definitions of E. E is a number that denotes the positive real number such that we can get natural log of E is 1 to E of 1 over t dt. So if I graphed out 1 over t and came up with the area under the curve from 1 to E, I would get that the natural log of E is 1. Logarithmic properties, if a and b are positive numbers, we have covered these properties quite well earlier in chapter 3, I believe it was, where E to the 0 is 1. And if I have multiplication, I can change it into two separate natural logs. That can be a real benefit when you're taking derivatives. We can get around the product rule. The power rule says this n can come down front. And that can help us because we don't have quite as much chain rule to deal with if we're taking the derivative. And quotient rule can be huge. Divide up into two separate natural logs. I'll let you read that on your own. So derivative of natural logs, we worked with these earlier. If you remember, the derivative of natural log x will be 1 over x. And we must insist that x be greater than 0 for that domain of x. And secondly, if u happen to be just like a function instead of just a simple little x to the first power, if u was something a little bit more like natural log of 2x, well, how would we deal with that? We would say it is 1 over u times u prime. Here's where we pick up the chain rule. But otherwise, it's 1 over the object, like 1 over x, in this case, 1 over u. That's what is being described in that verbiage. All right, sketch the graph of the function and analyze x plus 2. Well, we know for domain-wise, this together has to be bigger than 1. So my domain, I could figure out that x plus 2 must be greater than 0, or that means x must be greater than 2. There is our domain. Did I say negative 2? X must be greater than negative 2. The range, however, no matter what we put in for our domain, we will come out with a range that covers all real numbers, so negative infinity to positive infinity. I also know, like transformation-wise, transformations, that this thing is going to be slid horizontally. Let's see, it's going to move left by 2, isn't it? So we can see sliding left by 2. If I put in negative 2, I should get out. Am I off on that? Yeah, when we put in negative 2, that produces the 0, doesn't it? And there we have our vertical asymptote. So where we had a vertical asymptote at 0 before, it got slid left by 2. So that makes sense. Where we had our function coming through at 1, when 0 hit, we had passing through 1. Now it was, when we were at 0, we should now have e to the, or what am I saying? To get this to be 1, I would have -1 for x. So -1, 0 is a spot. All right. This was going through. There we go. Now, there. That's what I knew. It wasn't looking right, guys. So, yeah, when it used to go through 1, natural log of x, when x is 1, we get out 0. And so there was that spot. Now, transformation-wise, natural log of x plus 2, this point goes back to slides to the left 2, and there we hit it. All right, next up, logarithm rules. We already covered that. So let's do some derivatives. Natural log of x squared plus 2. This is going to be treated like my u, and I know the pattern is u prime over u. So to take the derivative, we want to look at u prime over u. So I'm going to have 2x over x squared plus 2. Simplifying, nope, there's no simplifying that can be done. I cannot reduce my x's because of this plus 2 hanging on there. Next one, let's rewrite this function as y equals natural log of x squared minus 9 to the 1/2 power. That allows the power rule. We can go 1/2 natural log of x squared minus 9. And the power rule allows us now to take the derivative and just focus in on what the derivative of this would be. So I'm going to have u squared minus 9 as my u. That'll give me a 2x over x squared minus 9. In this case, since we have two groups multiplying, this 2 may cancel into that 2. 2 divided by 2 gives me 1. I end up with x over x squared minus 9. Natural log of natural log. These are always a little bit tricky. And we need a u prime over u. And in this case, our inner function is our u. So we're going to have a natural log of x, its derivative over the u portion. And that should be our y prime. So following through this, with this, I have 1 over x divided by natural log of x. Well, that's like a natural log of x over 1 and a 1 over x. We can simplify this down by going 1 over x times the reciprocal 1 over natural log x. And our answer will turn out to be 1 over x natural log x. Think that through again. We allowed the inside part of our natural log to be u. And we know the pattern is u prime over u. So here was my u, so I'm going to need to take its derivative. But its derivative turns into 1 over x. So it was u prime over this u. Follow it through. Number D, letter D, y equals, let's break this up using our division property of natural logs, the quotient. And it will look like this. So this is just natural log properties being utilized. And now we're going to go y prime is equal to u prime over u. So I'm going to end up with 3x, derivative of 3x, which is 3 over 3x, minus derivative of the top is a 1 over an x minus 2. Over here, I get reducing and I have 1 over x. So let's just write this a little bit more cleanly. 1 over x minus 1 over x minus 2. I would like you to practice pulling those fractions together because I suspect you will need to be able to do that for multiple choice answers in the AP exam. Of course, we need like denominators, and that like denominator will mean that each of these fractions needs the other denominator. Pulling it together, we're going to have an x minus 2 over this x minus 2. Minus sign, so minus sign, x on top, and there's that common denominator that we brought in. All right, simplify the top. We're sitting with y prime equals x minus x is a 0, so a negative 2 over an x minus 2. final answer. Practice those. Practice on making like denominators. This one says, find the slope of the tangent line to the graph of the logarithmic function at the point 1, 0. Well, keyword to me was, let's find a tangent line. The slope of the, we just have to find the slope of the tangent line. Oh, not even the equation, huh? Not too bad. To find the slope of the tangent line, I need to get a y prime. That'll give me the slope. And then I'm going to evaluate it at 1, coming from that information. So we start with this y equals natural log of x to the 3/2 power. But that 3/2 can be slid down front, and I'm going to have y equals 3/2 natural log of x. The derivative then is quite simple. U prime over u, or the derivative of x, is 1 over x. And y prime equals a 3 over 2x. To get the slope at a point, the slope at the point 1, 0 means I'm going to have y prime evaluating at 1, the x value. Plug it in, 3 over 2 times 1 gives us 3 over 2. There's our slope at 1. Number 4, find an equation of the tangent line to the graph of that equation this time of tangent line. So I'm going to have to do what I did before on the last problem, and that is get the slope. So let's start out by getting the slope. Well, f prime is going to equal 4x minus 1 over x, the derivative of natural log there. We need to evaluate the slope when x is 1. So we have 4 times 1 equals 1 over 1, which gives us, minus 1 over 1. 4 minus 1 is a 3. F prime of 1 equals 3. That is the slope that we're interested in. And we also have a point given to us as 1, 2. Equation of a tangent line, if you recall, is y minus y1 equals the slope evaluated at that x1 point, x minus x1. That gives me y minus 2 equals 3 x minus 1. That's a good enough format. Leave it there. Looks good. Number 5. And this looks like our last example. Find dy dx by implicit differentiation. Well, hopefully you recognize dy dx as taking a derivative. So we will have a little implicit. We can see these y's. It would be nice if we could solve for y, but that just doesn't look feasible. So let's take our derivative with respect to x. We're making x our independent variable. So the first one will be 2x minus 2. The derivative for a log is u prime over u. So y, the derivative of y is 1. And then I'd have dy dx over y. Plus, derivative of this, 2 comes and multiplies. We're going to have 6y to the first dy dx, since y is not the independent variable, and the derivative of 8 is 0. Let's subtract our 2x, leaving the dy dx's on one side. Remember, when we're in this mode now, we're just solving for dy dx. And that's going to give me negative 2 over y dy dx plus 6y times dy dx equals the negative 2x. I notice we have a GCF. Let's GCF out our dy dx. So dy dx negative 2 over y plus 6y equals a negative 2x. Finally, we can solve for dy dx, and I'm going to have dy dx. I was just looking at that. That's rather messy, isn't it? Before I do that, I'm going to clean this up. I want to make this into a like denominator. It now has 1, so let's incorporate an extra y in there. That'll give me dy dx is negative 2 over y plus 6y squared over that y. So common denominator is y equals negative 2x. There, that looks better. Now dy dx Dividing by a fraction is like multiplying by its reciprocal, so I'm going to reciprocate and have y negative 2 plus 6. And I think you probably noticed it too. What do we got? We got even numbers. So we should simplify this. Let's pull a 2. Let's pull a negative 2. That'll leave us 1 minus 3y squared. Check it out. Does it bring me back to negative 2 plus 6y squared? Yes, it does. All right. 2's will cancel. Oh, negative 2's will cancel. So plus plus on that, and then 2's are canceling. What do we end up with for an answer? A dy dx is equal to an x times y over a 1 minus, sorry about that, 3y squared. Boom! Hit the answer. Okay, that was a quick review. Some of that we've done before. Maybe not the implicit with that, but a lot of the others we've done. So you have a worksheet, 1 through 24, I think it is. And please have that done for class. Have a great day.